Huh?
Can you scroll down a bit? Yeah, that's fine.
Yes,
This
that's
is fine.
okay now.
Yeah. Okay.
This is fine. So if you allow, should I start with the introduction and then we can start with the lecture?
Sure. Well, I'm ready. No problem.
So Assalamu alaikum to all the participants and our resource person for today's Comstech Distinguished Scholar Lecture on Tapping into the Full Potential of the Stratosphere. Today we have with us Professor Dr. Muhammad Slim Luini from the King Abdullah University of Science and Technology, KAUST. And he'll be giving you a lecture on the high altitude platform stations and going into further details of their operations, why they are important, and paving way for a more connected world. So to give you a more detailed introduction to our resource person here today, I would like to invite our advisor here at Comstech, Professor Dr. Shahid Beg, to welcome and introduce the speaker for today's lecture. Over to you, sir.
Thank you, Asif. Assalamu alaikum and a very good afternoon, everybody from Comstech Islamabad. It's my pleasant duty to introduce Professor Dr. Muhammad Salim Al-Oni. He was born in Tunis, Tunisia. He earned his PhD from the California Institute of Technology in 1998 before serving as a faculty member at the University of Minnesota and later at Texas A&M University at Qatar. In 2009, he became a founding faculty member at King Abdullah University of Science and Technology, where he is currently serving as the Al-Khwarizmi Distinguished Professor of Electrical and Computer Engineering and the holder of the UNESCO Chair on Education to Connect the Unconnected. Dr. Al-Uni is a fellow of the prestigious IEEE, Optica, and SPIE. His research interests encompass a wide array of research topics in wireless and satellite communication. He is currently particularly focusing on addressing the technical challenges associated with information and communication technologies in underserved regions and is committed to bridging the digital divide by tackling issues related to the uneven distribution, access to, and utilization of ICT in rural, low-income, disaster-prone, and hard-to-reach areas. It is now over to Dr. Al-Uni. Please, the stage is yours, sir.
Thank you very much for the nice introduction. Thank you also for the invitation and for giving me the opportunity to share with the audience here some of our recent work. Given the expected nature of the audience, I would expect the audience to be a little bit, I would say, general audience, not like very technical in my field of expertise. I try to make the presentation as accessible as possible, but of course, at the end of the talk, we can reserve some time to ask questions to have hopefully a better understanding of what we are trying to do here. So, as the title indicated, the presentation is about how we can take advantage of the stratosphere. So for those of you who don't maybe know what the stratosphere is, it's a certain layer of the atmosphere above the troposphere, so roughly 20 kilometer altitude. And it's expected that this layer will become hopefully useful in the near future for a variety of applications, as I will hopefully convince you at the end of this talk. So, but just to kind of tell you why I'm looking at this, at least from my perspective, I am a researcher in the area of wireless and satellite communication. These days, those of us who are active in this area are very focused on beyond 5G system or 6G, meaning by that, like the next generation wireless communication networks, which are of course expected to kind of continue pushing the envelope in terms of going to higher speed, lower latency of transmission, more massively deployed IoT device for industrial and environment monitoring type of applications. But another important aspect that 6G is going to do, or at least is said to do, and by the way, 6G is expected to start being deployed by the early 2030s, so like about 5 years from now. But already we start having a vision for this 6G. ITU, which is the United Nations agency in charge of telecom, already have a document called IMT 2030, which kind of give an idea of what we want 6G to deliver. And another important aspect, as I mentioned, that 6G would like to deliver is to bridge the digital divide or the connectivity divide. As you may know, we live in a world where about 1/3 of world population is still unconnected or underconnected. We are talking about 3 billion people, mostly living in rural areas, low-income neighborhood, disaster-prone areas, etc., etc. So many of these areas are suffering from this connectivity divide, and the idea is to try to help this area by bringing connectivity to them and hopefully bring prosperity to these area that are deprived of connectivity at this point. So, in a nutshell, 6G is continue to improve what we were able to do in previous generation, but also we want to see more energy efficiency. We want to see more security and privacy in our network, more digital inclusiveness, like this digital divide aspect, and more resilience, robustness, and dependability. That's an important aspect that we'd like future networks to also meet, in the sense that, as we all know, we now are really dependent on our network, on our cellular phones for day-to-day transactions. And when you have an outage or our phone don't work, really a lot of daily operation are not possible anymore. So it's like power outages have been for a long time very critical. I think network outages are becoming as critical, so that's why resilience is becoming an important aspect. So in this context, when we talk about this connecting the unconnected and making sure to bring connectivity to these rural areas, we are actually also solving many other problems, in particular the resilience problem, because let's assume you have an up and running network, but then suddenly you have like a natural disaster or a man-made catastrophe like terrorism attack or something like that. So obviously overnight, you may have basically a completely unconnected zone because all the base stations are not functional anymore. And in this case, that's why bringing connectivity typically from the sky in the form of satellite or like as I mentioned now, drones or things like that we'll be discussing, is the way to go to bring resilience and to bring connectivity in post-disaster emergency type of situation. Similarly, if you send explorer or people like in adventure situations in the middle of nowhere, like scientists, let's say, going to the Amazon or to the mountains, and you want to video stream information real time, you are in a way solving a connect and connect type of problems. Military missions tend to also operate in unconnected environments, so they need this connectivity in hard-to-reach environments. Another important application is the fact that we are not talking only about connecting people. Sometimes it's as important to cover unconnected area and to basically bring connectivity to IoT devices for smart agriculture, environment monitoring in rural areas, in forests, in mountains, and so on. So it's not only connecting people, but connecting devices and sensors and actuators. Another important application is what we call offloading for basically urban environment that are hosting special events. So, for instance, you have let's say the final of an important football match or Olympic Games over a couple of weeks. So you need like a surge of capacity, but only for a finite amount of time. Again, instead of building permanent infrastructure on the ground, like extra base station, extra towers, etc., you can kind of keep your standard average type of capacity needs from the ground, and the extra capacity that you need, you can bring it from the sky, again from satellite links or from drones type of base station connectivity to help ground network or network in general deal with this surge of capacity. The final two applications are more the area of transportation systems. Many areas in the world are moving towards these kind of aerial network in the near ground space, like meaning by that using drones to transport merchandise or to even transport people in the form of flying taxis. So we'll be having eventually in our cities these kind of vehicles flying at a few 100-meter altitude. In other words, we are not talking anymore about two-dimensional network where the network is only consist of ground users. We have three-dimensional network where we have users on the ground at few 100 meters, and we need to kind of cover everyone and connect everyone. And again, connectivity from the sky can be the way to go. And finally, connecting boats, ships, since waters cover 70% of the Earth, and it's of course impossible to create base stations like in these kind of isolated and far maritime environments. So you need to connect them from the sky. So this connected and connected that is coming from sky connectivity or satellite connectivity is basically helping, of course, connect the rural area, the hard to reach area, but also is helping in many other contexts. So the main problem why we need like this connectivity from the sky is summarized in this block diagram, where you see here basically this diagram showing quality of experience as function of the cost per user in remote low population density areas. So we know, for instance, that fiber optic is the way to go for urban environment, but fiber is not really economically viable for rural environment because it does not make much business sense to dig and lay hundreds, if not thousands of kilometers of optical cables to reach these remote, low population, often low income areas. So basically, there's no return on investment, and MNOs or mobile network operator are not very motivated to deploy optical fiber in these kind of conditions. So you want to go to satellite, but classical satellite, like the one that we were developed initially, are mostly for broadcasting, one-way communication. As soon as you start talking about two-way communication, like uplink and downlink for internet surfing, like or browsing, like we have with Starlink, it's completely different design and it tends to be more expensive. So we need to go along these lines of Starlink type of solutions, but we need to have them in a cheaper way. So we are basically going after this upper left corner where we have global connectivity anywhere in the world, but basically at a low cost, even for low population density area, in order to achieve this nice vision that Tesla had for the world in terms of connectivity 1 century ago. If you read the statement very carefully, you see that Tesla was thinking about this kind of inexpensive receiver able to communicate anywhere in land or sea at any time. So that's kind of the vision that really we have. So, one first kind of idea that can come to our minds, instead of going to the sky and to the space, you can still try to use the kind of mountains and hills that we have. Many of these mountains and hills have towers, TV towers. So if you can capitalize on that by attaching to TV towers base stations, cellular base stations, then you can have relatively wide coverage of few tens of kilometers. Actually, this is a very simple idea of recycling, in a way, TV towers to become also base station for telecom, and with the right amount of power, try to kind of cover wide areas. So, like with one of my former postdoc, actually, we did a quick study on this. So we looked at Ethiopia, which is one of the countries that suffer most from digital divide. So there's one particular province in Ethiopia where you see different dense population. Yellow is very, very small dense population. Green is higher. Blue is relatively high dense population, and that's why the blue area corresponds to cities here. You have two base stations in red, and then with these two base stations, about only 5% of people are covered in this province, so very low, basically, penetration in terms of connectivity. Now it happens in this province, they have 3 TV towers in black. So if you choose now to equip the TV towers with base stations, right away you move from like about 5% to pretty much 14.25%, basically connectivity rate. So you really improve by 10%. And if you decide to move a little bit your TV towers to basically location where there is higher density populations, then you can jump all the way to roughly 20%. So obviously you are not going to like a 99 or 100% coverage or even 90% coverage, but yeah, with this kind of terrestrial solution, still you are able to improve by taking advantage of these basically TV towers. Now, obviously, if you want to extend your coverage and go for basically more than tens of kilometers, but like more of the hundreds of kilometers of radius of coverage, you need to start having base station attached to aerial or space platform. So as I mentioned earlier, probably you have heard about Starlink as one of the most recent satellite solution to bring connectivity worldwide. And Starlink is not the only project. There are many other competing projects. In the US itself, there is another competing constellation in the making, and they start launching it. It's called Kuiper. It's owned by Amazon. So it's a kind of a competitor for StarX or Starlink. There is a Canadian Lightspeed. Europe is having also a constellation called Iris. And then basically the Chinese have JW and G60 as basically emerging constellations. So it's a race in a way. Everyone's trying to bring this global connectivity through satellite because it's a mature technology by now. It used to be kind of a challenge a few years ago, but then there was a breakthrough on how to kind of manufacture at low cost these satellites, and now we're able to mass produce them, and that's why there is this race now towards basically global connectivity via these mega low Earth orbit constellations. But actually, I would like to argue that there is a room for other ways to connect the world from the sky without having to go to the space, meaning by that through the stratosphere, as I mentioned earlier, at 20-kilometer altitude. So what we can launch in the stratosphere is what we call high altitude platform station, in short HAPS. HAPS can be used as an acronym also to describe high altitude pseudo satellite. So these are like satellite, but at a much lower altitude. They are quasi stationary. They are not on orbit because they are not in space. They are still in the air. They can come in the form of balloons or airships, or these are basically lighter than air type of platform, but they can be also heavier than air platform, meaning by that like more like a gliders or aircraft, like what you are seeing here on your left. So there are many companies trying to kind of develop these hubs, and the vision is that basically we will have an infrastructure in the stratosphere, a tower at 20 kilometers that can help with connectivity. For instance, here we have like let's say a disaster or a flood region. We have people who have moved to this refugee camp, so hubs can be used as a base station to cover or to bring connectivity to these people. But perhaps as a tower in the sky can have a radar to, let's say, measure the level of water, can have a camera to basically be used for border control. You can have a LiDAR for advanced monitoring. So basically, it's a kind of an infrastructure that can have multiple missions, connectivity being one of them. Of course, a HAPS is a relay. So at the end of the day, the information that come to the hubs or leaves the hubs has to be relayed to the internet. So the hubs has a feeder link or a backhaul, like you see here, a backhaul to the ground using free space optic. I will talk more about that towards the end of my talk. Also, alternatively, the hubs can be backhauled via feeder link going to a satellite constellation. So either way, it can be either to the ground or to the space. So the HAPS has a lot of advantages. So, I can mention two of them at least. Number one of the key, basically, I would say, challenge that all satellite constellations are trying to solve is what we call direct-to-device communication. How we can connect directly our standard phones, not special satellite phones, standard phones, the one we use for 4G, 5G connectivity, to a satellite. That's everyone's trying to do that. Some of them have been achieved, but only for low data rate, like SMS type of application. If you want to go to higher data rate, it becomes very challenging. You need antenna that are huge at the satellite level, or you need to use like distributed antenna system from multiple satellites. So basically, the whole thing is quite complex. The idea is that the hubs can a natural way to connect people on the ground because they are only at 20 kilometer altitude in contrast to LEO satellite that are at 600 kilometer altitude. So being closer, the budget link makes it that the signal to noise ratio is much more friendly, is much more favorable for direct to device communication. So that's one advantage. The second advantage is sustainability, let's say advantage or argument. You know, as I told you, it's becoming a race. Every country is trying to launch its own constellation. There are limited orbit spots, and space is getting congested. And this can lead to basically a very well-known paradigm that has been kind of described in a NASA technical report in 1978, where basically you can have a full collapse of this constellation with collision. So, I mean, the whole thing can start by one collision between two satellites. This collision can generate debris. The debris can generate extra collisions, and basically, subsequently, all these successive collision can basically lead to a collapse of all these constellations. So, whereas HAPS, at the end of the day, it's just basically an aircraft. It can go for a mission. Of course, it can stay for weeks or even months, but then it can come back. It's not like a satellite. Once it's launched, it's kind of over. You cannot get it back until the end of the lifetime of the satellite. HAPS is like an aircraft. It goes and it comes back. When it comes back, it can be maintained. It can be upgraded. Eventually, it can be retired. So you don't have to deal with like space debris like the problem is with satellites. So in other words, what we are arguing is you can have a variety of. Oh, I think there is a question by Madiha. Madiha, do you want to ask a question now? Madiha, Rayhan.
Sir,
I see a raised hand.
at the end of the lecture, we can take questions 5-10 minutes altogether. So you
At the end of the talk, you mean, huh? Okay. So the argument here is we can have base station at different altitude for different coverage area. So of course we are all familiar in a kind of urban or downtown type of environment. You put base station on the top of towers. If you are in deep rural environment, maritime environment, you do satellite. But in between, you can be using a variety of other platforms, including HAPS for basically interesting, basically medium density type of population. And by the way, we have done some experimental work, and even some other company like Google, Facebook at some point have done some HAPS experiments. It worked quite well technically in our campus on the Red Sea, not very far from our campus, in collaboration with Deutsche Telekom, CST, which is like the regulator in Saudi Arabia. We have done some HAPS tests that have been documented in this paper. The idea is to do 5G connection direct from the phone to a HAPS. And we were able to show that when you compare connectivity coming from a terrestrial base station compared to connectivity coming from a HAPS, like with two base stations attached to a terrestrial base station and a HAPS, and a car moving away, at some point when the car is very far, the basically blue link, which is a terrestrial link, kind of dies from a throughput and spectral efficiency perspective, whereas the connectivity coming from the HAPS, the magenta type of curves here, have or maintain always a good throughput, a good spectral efficiency, even when the car is really far away from the base station. And that's the advantage of HAPS. It has a better line of sight probability, so it's less obstruction on the way, and you can have a much wider coverage. So the kind of research problems we do is to try to see the advantage of HAPS. So for instance, one of my students, she worked on this problem. She looked at basically a situation where you have ground users. These ground users, some of them are urban environment, some of them are rural environment. So those who are in urban environment, they can basically connect to terrestrial base station. Those in the rural, they don't have base station, they connect only to the hubs. And the question is, how much advantage do the hubs bring in terms of connecting these unconnected? So we did like an optimization problem. We took here like a particular illustration of how good are our results. So we have like, let's assume here a kind of a particular deployment where you have a town, you have a village here. This town have base station. These are the triangle in black. As you see within the town and this village, people are very well connected. These are like user served by base station with this kind of pink circles. But then when you move to rural area in between, you have less base station. These are the kind of triangle. The user in blue here, many of them are unconnected. So you see here, they are not circled. Few users are able to be connected. Basically by this terrestrial base station. We have a user here that is connected by a HAPS, that's a star, and the HAPS has still limited power. If you increase the HAPS power from -4 dBW to 10 dBW, you are able to connect more rural users. You have many users who are becoming star here because you are able to connect many more users. And eventually, actually, if you increase a lot the power available at the hubs, not only you are able to connect all the rural users with the hubs, you are able even to help some of the urban users who have a poor channel because they have maybe obstruction in front of them or something like that. And so the hubs can not only connect the unconnected rural area, but can in a way super connect or bring better connectivity to users who are in urban environment. So that's kind of a nice lesson we learned from this research and this paper published a couple of years ago. Now, another important problem that we had to solve when we start about hubs is a coexistence problem. Basically, the vision that we have and that has been kind of adopted by ITU is that the hubs will be using the same frequencies as the terrestrial base station. Why? Because we want the phone that we use are the same. We don't want to have different phone with different frequencies for hubs and different frequency for terrestrial network. So the same frequency have to be used for both. The problem is, of course, you can generate interference. So the problem we solved is we assume we have a big deployment, and this deployment we have many communities like cities, villages, and so on. Of course, within these communities, you do have base station on the ground, but you have always rural user in between. These will be served by these hubs. So basically, the idea is on the ground, basically what kind of performance I'm going to get depending on what do I connect to. So we compare two kind of systems, like what we call a coordinated system versus uncoordinated systems. We use, of course, like standard beamforming antenna patterns available in ITU, just to make sure that we have realistic type of assessment. So to do our comparison, we assume different kind of users. So we assume that there are what we call deep urban users, that they are the green user very close to downtown. Then we have the users who are the urban area inside, but they are far from downtown, more close to rural area. And then you have basically the users who are outside the city, but very close. They are rural environment, they are very close to the city. And then you have the deep rural users who are very far from the city and rural areas. So we have 4 categories of users. And we try to check the impact of this spectrum coexistence on basically these different category of users. So let's look at uncoordinated system. By uncoordinated system, we mean a system where basically you connect to a terrestrial base station if you are within the city, close to the downtown or far from downtown. As long as you are within the city, you connect to a terrestrial base station. If you are outside the city, you connect to a hubs. So before connect the hubs, just to check the performance of the system in Dash, which is without hubs, you see that the deep urban users are doing very well. The urban inside user are doing okay. The urban outside users are still doing okay because they still benefit from the base station that are still available very close by in the urban environment. But the rural user or deep rural user in magenta are very bad because there is no terrestrial base station pretty much outside the urban environment. Now, if you introduce the hubs and you start by connecting in an uncoordinated fashion, as I mentioned, as you see, the blue user, the deep urban user, maintain very good connectivity because they are still connected to the terrestrial base station. The border inside are still okay because they are still connected to the basically inside the terrestrial base station. But then you see a drastic decrease in the performance of the border outside because they start being connected to hubs, but they are subject to very strong interference coming from the terrestrial base station urban environment because they are still close to the urban environment and they used to be connected to this urban environment. And then, of course, the deep rural user take advantage of the hubs to start having a much better coverage probability. Now, if you go to a coordinated system where basically you don't connect anymore just based on your location, but based on the strength of the signal. So you compare the different signal coming from different base stations, different hubs, and you pick the best signal. In this case, what you see, everyone's doing much better. So even the users who suffered quite a bit from the introduction of hubs in this kind of shared spectrum environment, they move from this very bad performance to something pretty much like before. So the yellow curve has been recovered without losing the good coverage that we are offering now, the deep rural users. So hubs sharing spectrum with terrestrial base station in a coordinated fashion can really bring good connectivity to rural users without affecting urban users. Now, as the last part of my talk before we open the stage for questions, I would like to talk about another important technology that can come with hubs, which is basically a light-based technology or a laser-based technology known as free space optic communication. That's a well-known technology that has been kind of developed for initially terrestrial application. It's great. It can transmit a huge amount of data wirelessly because it's like a laser transmission over the air. But it is subject to many challenges in the sense that it's subject to weather condition impact. To point, the pointing has to be very important, very done very well. All of this made this technology really never pick up and become a massively deployed technology. But this technology now has an opportunity to flourish in the context of this non-terrestrial network, space, and aerial-based network. Why? Because as soon as you start talking about space network or aerial network, you start lifting base stations, then the swap constraint become very important. And by swap, we mean size, weight, and power constraint. Every time you lift something, you need to worry about how big is it and how much weight is it and how much power does it need. So the swap is an important aspect, and it turns out that free space optic or laser communication is very competitive from perspective. Why? Because basically, laser communication operate at very small wavelength in the optical band, so it tends to use much smaller equipment. It's much more energy efficient, and basically it is, from a weight perspective, lighter than a huge antenna that you would need to use if you want to use RF band. So that's one of the main advantage of free space optics. So in this context, basically, what has been proposed is a system that can rely on satellite or hubs to basically connect people on the ground using RF. So the user will still use their phone to connect to the hubs or satellite, but the backhauling, the feeder link, because at the end of the day, satellite or hubs is a relay. Instead of using RF backhauling in the Ka band, we would like to use these free space optic links, these laser links, to backhaul information in the order of hundreds of gigabit, terabit per second data rates to the ground. Of course, you need to deal with all kinds of research problems, dealing with pointing, dealing with atmospheric turbulence, dealing with weather condition like blockage here, like cloud blockage. You need to find solution to that, for example, using diversity. So you cannot live with a single optical gateway station on the ground. You need multiple optical gateway stations with the understanding that if the signal gets blocked by one cloud, it can be recovered by another kind of optical gateway station that is operating in a region that doesn't have cloud at that particular time. So this is an active research area now. Free space optic for non-terrestrial network is an emerging topic, and it has a very good potential. So of course, one of the issues that free space optics have to deal with is atmospheric turbulence, which is due to the random variation in temperature and pressure in the atmosphere, and that basically leads to the fact that you have random variation in the refractive index structure, which is the medium over which the laser beam is propagating. And because of that, what ends up happening, the laser beam, instead of remaining collimated and very focused, it ends up spreading and end up also wandering, which means at the receiver end, you don't have anymore this very sharp focused beam footprint, and that is fixed. It's kind of dancing around. So you need to kind of resolve this issue. So one technique that is being used is adaptive optics. That's a technique that has been used in the context of imaging and telescopes. It has been borrowed for communication purposes to try to clean up the signal and kind of mitigate the effect of turbulence. And that's an example how adaptive optics operates. So you take a beam, you kind of get it distorted because it went through a turbulent environment. If you adopt a post-compensation, you can clean up this beam. Similarly, if you start with a pure beam and you can pre-distort it, if you want to do basically the kind of processing with other optics up front to kind of save basically space and weight from the receiver end. You pre-distort it, and then when it goes to the beam, to the medium, you end up getting the nearly pure beam that you are aiming to get. So we're able to analyze the performance of these systems and derive some closed form expression for the outage probability for these kind of systems in a paper published a couple of years ago. And you see here the comparison with and without adaptive optics. So like when you look at the blue curves, the one diamond is like with adaptive optics, and that gives you much lower outage probability, which is great. Same thing for the red, which is the downlink, which is like basically the downlink being like from the, let's say, the hubs to the ground. And then the horizontal link, which is hubs to hubs, you also get a certain gain by using adaptive optics. It's also important to notice that a downlink always outperforms an uplink, which means a hubs to ground performance is better than hubs to ground to hubs, not reciprocal. And this is due to the fact that basically you tend to have, let's say, more atmospheric turbulence towards the ground. And when you have an uplink, right away you get hit by the strong atmospheric turbulence that degrade your performance. So one way to mitigate that also is to use MIMO system, multiple lasers and multiple detectors. We had this paper where we showed that basically you can have a lot of gain. So this is like the outage probability as function of the SNR. A one-by-one system will perform here, which is bad. And if you want to improve, to go to the left, you go by, let's say, a 2x2 system, and you see the 2x2 system perform much better than a 1x1. So it's like instead of one laser and one detector, you use two laser and two detector, and with that you take advantage of diversity to improve the performance of your system. Of course, this is under the assumption that the performance gain is achieved when you assume you have basically complete independence from the different propagation path. In practice, there is some correlation. We had a paper where basically we quantify that, and we showed that there is degradation performed because of this correlation, illustrated in the graph in the figure in front of you. So finally, what I would like to mention in the context of FSO, hubs and satellite can collaborate. Indeed, the hubs can act as a relay because, as I mentioned, free space optics can be degraded quite a bit by atmospheric turbulence, especially towards the lower part of the troposphere or the atmosphere. So if you put the hubs in between, basically clean up the signal and re-forward it, then basically you can get much better performance. So we showed here in our analysis that basically when you compare a direct link to a relayed link, you see the direct link in blue here has the highest outage probability, which is bad, whereas a relayed link will start gaining, especially if you place optimally the hubs on the top of your ground station, minimizing the distance over which the free space optic links has to propagate in the troposphere. You end up having the lowest outage probability. So bottom line, this is our vision for the future in terms of how we can capitalize on this stratospheric layer. It's a layer where we can deploy a fleet or a constellation of hubs, interconnect with free space optics. Each hubs can be also backhauled to the feeder link via feeder link to the ground or to the space or to another hubs. And then basically these hubs can be used among many other applications to connect people on the ground or device on the ground. So it's like connecting people and IoT. And they will be acting like satellite, but instead of operating from space, they will operate from the stratosphere. So with that, I would like just to re-emphasize that for beyond 5G and 6G, non-terrestrial network are becoming a very important application, a very important technology that has multiple application for rural connectivity, post-disaster situation, connecting airplane and ships and urban offloading. There is an opportunity to do a lot of research in emerging and interesting new wired technologies in the context of non-terrestrial network, and some of these are listed here. So with that, I would like to conclude, and I would like to leave some time for the Q&A part of this presentation. I would like to invite you to follow some of our research papers in our group webpage, CTL. You can see the link here. I always ask my students also to develop video articles that are posted on YouTube. So if you go to this YouTube channel, you can see many of our research activities described in the form of a small 3-minute talks by my students. And actually, given our interest in this general area of connected and connected, we established a UNESCO chair within our group focusing on this topic. And we have a LinkedIn webpage where you can also follow some of our research papers and research news. With that, I would like to thank you, and I will be happy to take some questions.
Thank you very much, sir. So any questions, please just write them down in the chat and then Professor can answer them. There was an earlier question regarding the huge number of satellites in the stratosphere and its relation to space pollution.
Yeah, this is what I mentioned. Indeed, there is a risk of the so-called debris problem or space pollution problem. I mean, the satellites are not operating the stratosphere. The satellites are operating in the space beyond the stratosphere at 500, 600 kilometer altitude, but it's getting congested there. There are risks of collisions. At the end of the lifetime of satellite, basically, we have to deal with all this debris. So indeed, it's a problem. And that's why I believe that HAPS is a good alternative or a good complement to satellite, because as I mentioned, HAPS is like an aircraft. So basically it go on a mission and then it can come back. So it doesn't have to stay there. It does create space debris. Actually, it's like an aircraft, like an airplane. It goes, come back, can be maintained, upgraded, eventually can be retired. So obviously, the advantage of hubs is there compared to satellites.
Thank you, sir. So any more questions, just please write them down in the chat. We'll take a few questions now, and then later on, if anyone has extra questions, they can just email it to me and I'll forward them to you.
I see here one.
Yeah.
Yeah, go ahead.
There is one, but I'm not sure if it's related to the lecture, but if you would like to comment on it.
Okay, this is like the balloon in Brazil or something like that, right?
Okay, there's one. It says it's from Dr. Saqib Nisar. Could you please elaborate the role of the HAPS technology in energy efficiency processes?
Yeah, I mean, it's very simple. As I mentioned earlier, when we talk about direct-to-device communication, like what you're trying to do, you want to use your phone to communicate directly with satellite. You know, obviously, going through a 600-kilometer path is much more challenging than going through a 20-kilometer path. As simple as that. So you'll be more energy efficient. Your battery will stay longer if you have to transmit to basically a much closer base station. So you know, energy efficiency is clearly there because of the fact that the HAPS is, from a proximity perspective, much closer to the Earth than a satellite. So that's as simple as that. I mean, I saw another comment on this Brazil. In Brazil, apparently there was this kind of balloon that burned and people died. But all the HAPs are not meant to be, that I talked about, are not meant to be manned. They're unmanned type of platforms. So they are going there for, like satellite, for weeks or for a month on a mission, and they come back. I mean, they can collapse, the accident can happen. Of course, when they collapse, if they collapse in the sea or in rural area, I mean, it's not a big problem. Of course, you lose the HAPS itself, but of course, there is always a risk that they kind of basically kind of come down on a city and they can maybe kill people. But one good thing about HAPS, they tend to be very light. They are designed to be very light because they have to be also from a, you know, the heavier, as you know, is a platform, the more energy it needs to fly from proportional perspective, and that's why they design them very light. So it's not, again, like a big aircraft that is going to collapse and create a big damage on the ground. So yeah, there are always a risk when you have an aerial platform that accident happens, and but there is no people involved, at least from in the platform itself. It's an unmanned platform.
Okay, thank you so much, sir, for taking out the
Thank
time
you.
delivering this very important lecture. If there are any more questions, just drop them to me through an email, and I'll compile them and I'll share them with Professor for his comments. So once again, thank you very much, sir, and
Thank
we
you.
look forward to having further lectures with you as well. And this lecture is being recorded as well, so soon it will also be available on our YouTube channel for anyone to review or further disseminate to people that might find it of interest. So once again, thank you very much, sir, and thank you very much to the participants who have participated in today's webinar. For the certificates, I've dropped the email in the chat. So whoever is here, they can mark their attendance in the email given, and then we will issue you your e-certificates as well. Thank you very much, sir.
Thank you very much, and thank you, Hasib, for the invitation. Let's keep in touch for other activities.
Inshallah.
Thank you very much. Assalamu alaikum.